Okay. I do want to take your homework, but I've also realized that some of these problems we didn't quite get to be able to work through them in class. So I'm going to push the homework out again tomorrow. Hopefully, I can get through 6.2 and a little bit of 6.3, so you guys actually know what to do with your homework. So if you guys can turn to page 10 in your packet.
They call you.
Okay, I think we finished example 6, correct? If we do that, okay. Let me just run through number 6 again. The whole idea is that we want to isolate that summation I so that because we have a rule that can get us in terms of n. The whole point here is if I can get everything in terms of n, then I can use my limit properties to help me compare exponents and pull the coefficients, get down to my limit. So with number 6, we have 4i over n squared. I like to push the portion that is unchanging. Well, not unchanging, but we're trying to get everything in terms of n. So the 4 over n squared is ready to go. It's just the summation I is not yet resolved. So we want to resolve that expression, get it down to the rule that is useful to us, and then we can find the limit. Now, example 7 is a little more involved, but same idea. If I can clean all this up and I can identify the portion that my summation rules will apply, then I could go ahead and do that. So first thing though, I'm going to see if I can FOIL all this mess out. So this is 1 plus 2i over n. Let me FOIL this out first, and then I'll deal with that 2 over n. So I get 1 plus 2i over n plus 2i over n, which is 4i over n. And all this, I will distribute the 2 over n through. All right. I want to make sure that each gets its own summation treatment here, or summation rule. And as I do that, I also want to begin to separate the parts that that don't have to change. So my 2 over n can be pushed out. I know it's a summation of 1 that's going to have the rule that I can apply to this. And then with my second term, I'm going to pull the 8 over n squared out. It's just the summation of I have to worry about.
So you can't take out all the n's at once, or
You mean factor out all the n's?
yeah.
We could. I just find that it's a little bit cleaner to just do it this way. So then, so I don't have to do with I like the idea of having separate things rather than having them all connected. It just feels easier to me. So this feels pretty structured now. I just have to worry about, okay, what can I turn this into? And I'm just going to change what I've identified as something that I can use my summation rules with. So summation of 1 turns into what? N. Yeah, you look at the previous page here, we have our rules. Right, summation 1 is n, summation I is this rule, summation I squared is this rule. Summation I is just n times over 2. So, right, and then summation I squared. Right, this looks like a mess to do, but if we just focus on the highest degree, then it's not too bad. So this one is pretty obvious, right? 2n over n, that's just become what? 2. This one, I could fold everything out. It's not too bad to distribute everything through, but I just wanted to say that we can get away with not even distributing that 8 through that second term, because we only care about the highest degree and its coefficient, right? Whatever this is, it's going to be a lower degree. It's just going to wash out. This will turn into what? 4. Okay. Now I could have just done that. It's not a big deal, but I really feel like this one, we can fold everything out, but if you just focus on what will produce the highest degree and the coefficient associated with it, just look at the first term of each parentheses, and you know that will be your highest degree term, and everything else is just going to be a lower term, which we don't care about. So if I multiply the 8n, n, and 2n, what does that give me? 16n to the third. Now, there are obviously more terms, but all the other terms have a lower degree, and we don't care about those coefficients, right? We only care about the highest degree. So this will just give me 16 over 6. So I have 2 plus 4 plus 16 over 6, and that's my answer. So 2 over 1 is 2, 8 over 2 is 4, 16 over 6 is 8/3. We use our calculator, or we can do this by hand. Ends up giving us an exact value of 26 over 3. Now, we mentioned this before, that we can continually improve the area approximation by increasing the number of rectangles. So if you compare 2 rectangles to 5 rectangles to 10 rectangles, you can begin to see the accuracy improve, because less and less gaps will occur, right? Let's say we have 3 curves here. These are the same curve, and we're using rectangles. Let's say this is a left-handed rectangle. You can see that obviously with one rectangle, you have all these portions that's out of your approximation. This is not a very good approximation. With more rectangles, you're getting better approximation, but obviously there's still gaps. And then with 10 rectangles, you can see the gaps are still there, but it's a lot less than before. So the idea is, well, what if we just continually improve or add the number of rectangles? Then our approximation will improve and improve better and better. So that begs the question is, well, what if we let the number of rectangles go out to infinity? Then we should have something better than the approximation. We will achieve the actual area under the curve. Okay, so that's the idea. Yes.
What was the thing that we just did there?
This right here?
Yeah.
This is kind of like a precursor to what we're going to do next. So this is like making sure that we know all the algebra, so that when we get to the rule involving infinity, this will feel familiar because we've seen it already. So right now, this doesn't mean anything to us. It just feels like, oh, it's just exercise, right? But we're about to see how this plays a role in this idea of increasing number of rectangles to infinity. Okay. All right. So if n approaches infinity on the interval from A to B, what is the width of each sub interval approach? As n approaches infinity, the rectangle width approaches 0, right? So imagine you have these infinitely thin rectangles that will adjust to every change of every point on the curve, and you can imagine infinite number of rectangles will achieve actual area of the curve under the curve. All right, so there's this area definition, which I want to go over, but I think it's easier to go over this once we have something that has more concrete. So first, we now have a new notation that we're going to use over and over again, and this is the definite integral notation. This basically is an area under the curve notation represented by this integral, this kind of this F notation, F looking notation. So this basically tells us that I want to find the area between the f of x graph and the x-axis between my endpoints A and B. So this will achieve the area under the curve. But for this one here, it says approximate the area using 4 rectangles on the interval from 0 to 2. So I want to show you the picture of, or not picture, but I want to show you what the approximation looks like. And then let's see if we can find the similarity between the approximation and the exact area under the curve if we were to push that n out to infinity. So if I want to approximate the area under the curve using 4 rectangles, this is my n value. And then my interval are my A and B values. Now, the width formula is B minus A over n. So 2 minus 0 over 4. What does that reduce to be? That's just the width of what?
1/2.
1/2. So we're going to say this. The integral from 0 to 2 of x squared plus 1. Right now, we still don't know how to find the exact area, but we'll use that squiggly equal sign to indicate that we're just doing an approximation of the actual area, because obviously this is not the exact area using 4 rectangles, because you see all these gaps that's preventing us from getting the exact area. But you know that your width is 1/2, right? So let's see if we can find each of the subintervals that we're going to use. So I'm going to start at 0, and I'm just going to manually find my next interval. So my next interval is what? 1/2. Okay. Next interval after that, 1. Next one,
3/2.
next one, 2. Okay. We're about to discover how the limit definition area is going to do all this for us. But right now, we're incrementing to the next interval on our own, right? So we're just adding 1/2 to get to the next interval, right? Now, this rectangle is actually using the left endpoint. So what's the width of my first rectangle? Okay. What's function notation to represent the height of my first rectangle? F of, well, first rectangle, F of 0, okay. All right. Next one, 1/2 times F of 1/2. Right, 1/2, right? Because that's my second rectangle, okay. Third rectangle, 1/2 F of 1. Okay. Last one, 1/2 F of 3/2. We're not using the last one because we're doing left-handed rectangles. So now I'm going to fill these numbers in for us. If I want to find the actual endpoints or a y value, they would get inserted into x squared plus 1. So plug in 0, I get 1. Plug in 1/2, I get 5/4. Plug in 1, I get 2. Plug in 1/2, I get 13. Sorry, plug in 3/2, I get 13/4. And that just gives me some approximation. I know this is an under approximation because all my rectangles are below, but does this process make sense, right? This is only using 4 rectangles. Right. Now, here's the structure that we're going to use that will help us get to infinite numbers of rectangles and finding the exact area. This is finding area using limit definition. Notice that every rectangle that we built had a width and a height component, right? You got the 1/2, which is the width component, the f of 0, f of 1/2. Those are all your height components. So we see that showing up here. You got the width component here.
Is that whole thing equal to the integral? Or?
That's right. This whole thing is equal to this integral here. Right, because we're actually going to achieve the actual area. Now this is function notation that represent the heights. Now this whole process looks messy, but I just want to show us that we've been doing this on our own because we found the width, right? And then we found the endpoint, which is 0, and then we kept adding the next interval over and then plug the function in, right? We did that all by hand, right? We found the 0, the 1/2, the 1, the 3/2, and we plugged into the function f of 0, f of 1/2, f of 1, and 3/2, right? But this is trying to do it all in the same move, right? It is finding the width, plugging in, and it's finding the next interval over. So if this is 1/2, it's going to increment to 1 next, then 3/2, then 2. But obviously, the more intervals we have, the smaller the width and the more increments you got to go through. But I just want to convince you that this is basically doing what we've been doing by hand, but we split it up into 3 steps, but this is all self-contained into one. Does that make sense? Right. So that f of a just means that starts with the left endpoint and it increments to the next interval. So if it's 1/2, then it starts at 0, then goes to 1/2, then 1/2 plus 1 is 1, then f of 3/2, then f of 2. Okay. So we don't have to do all these calculations by hand because the limit will do it for us. We just have to set it up so that we can let the limit notation do the rest of the work for us. Okay, so let's try the same problem, but we're going to use a limit definition to actually find the area under this curve without all these gaps in between. So let me write the definition again.
Do we have memorize this? Or?
I'll give this to you. So what is my width? 2 over n. I don't know what n is because I don't want to restrict it to just to be a set number, right? I want that n to be flexible so that it can be pushed out to infinity. So my width is just b minus a over n, which is just 2 minus 0 over n, which is 2 over n. I'm just going to fill in one piece at a time. What's my a value?
It's
0. That's nice. That makes my algebra steps a little bit easier. I can drop that 0. So I have my width component and I have my height component. So we can't do the limit portion until we get that out of function notation, right? So we're going to plug that 2 over ni into the function. So let me make sure that we do this. Let me structure it in a way so that you're not going to put that 2 over ni in the wrong place. So I would suggest that we do this first. Build your function without the x in it. And that way you leave the appropriate space for your new argument. So I'm just rewriting the function, but purposely leaving the x out of it and putting parentheses around it. So now if I want to find f of 2 over ni, I can just put them in the right space without accidentally putting it where it's not supposed to go. Okay, are we good so far? Now, this is going to represent it's going to handle all the increments for me. It's going to find my next interval for me. It's going to plug in the value for me. So that will go in place of this. So this is now going to replace this, right? I'm able to get that out of function notation. So I'm moving closer towards the place where I can use my limit as n approaches infinity. So now this takes us to the problem that we just did before, or similar to it, right? Where we just have to get this all cleaned up, involve the summation rules, and then eventually get compare degrees and look to see what that value is. And whatever this value gives us will actually be the area under the curve rather than just some approximation like 3.75. Okay, I can distribute this. We can fold this out and distribute this through here. So this becomes 4 over n squared I squared plus 1. Distribute that through. I'm going to separate these into its own summation so I can clearly see what rule is in play. I'm going to push the parts that I don't have to change. I just have to worry about my I squared. Sorry, n, not. So we know we have a rule for summation I squared. We got a rule for summation 1. Summation I squared. And we're doing the limit as n approaches infinity, so we only care about the highest degree. So we can just build what will be my first term. So my numerator is just going to be what? Yeah, not 8 over 6. There's something else here. What's 8 times n times n times 2n?
6.
16n cubed over 6n cubed. I do want to confirm that my degrees are the same, and they are, so I know I can just take the ratio of the coefficients. So 16 over 6 plus 2. Yeah, 14 over 3. Mm-hmm. Because we know that all the other terms will have a lower degree, and a lower degree is not going to matter. So, so right now it's this, right? If I follow all this out. And 2 plus. Right. We just take the ratio of the coefficient. Everything that's lower, it's just it's not going to have an impact because it's not growing fast enough for us to for it even to matter. So it just drops out. We just always take the ratio of the highest degree. Right. Okay, next page here.
So when writing it out, I can just like ignore the other terms.
Right, because we always take the ratio of the
Oh, yeah, like,
highest degree.
I was just wondering, like, would I be like taking points off for that?
No, I'm just if you recognize those are not even going to matter, we can just not even worry about expanding those out. That's why my shortcut is let's not even worry about the whatever is lower than my highest degree is just going to go to 0. It's going to just wash out. Okay, let's just try example 1. Just see if we can put it into this notation, and then we'll worry about cleaning it up a little bit later. But I want to make sure that we can set it up correctly. So it says rewrite the definite integral using summation notation. So we know that from this integral notation, we can pull the a and b value. And then this is our function that we'll use to build and find our y values. So again, what are the a and b values for this problem?
2 and 6.
2 and 6. My a is 2, b is 6. Okay. I can build my width formula, right? My width formula will be part of my, well, this is my width component. My width component is also within my height component because it's going to have, I have to increment to the next interval to plug into the function, right? That's how I got f of 0 and f of 1/2 and f of 1 is through this counter that is taking me to the next x value over. So what's my width here?
4/n.
Yep. So I'm just going to replace into my formula here 4/n, and I'm not going to write it here yet because I'm still in my cleanup stage here. F of, yeah, so I'm starting at 2, and then I'm incrementing by 4/n to the next interval. It's like if this is 1/2, then it'll be 2 plus 1/2 plus 1/2 plus 1/2, right? Getting to my next interval to plug into my function. But here, it's going to be more abstract, but it's still the same idea as 4/ni. So how do we get this out of function notation? Well, let's go ahead and make sure that we don't put that 2 plus 4/ni in the wrong place. So if I rewrite my function with the parentheses in place of the x, then I'm not going to put my argument in the wrong spot, right? So my 2 plus 4/ni will just go directly into these spaces that I reserve within my function. So if I were to put it all together, this is my limit notation. And then the rest of the work is just foiling everything out, distributing everything through, cleaning everything up, and then separating each of your summation terms and converting them in terms of n. But right now, let's just focus on making sure we know how to set up. The hardest part, I think, is just making sure that we know where that argument goes, that it goes inside the function and not outside of it, right? So if you have a reserved place for it, you're not going to put that argument in the wrong spot. one thing I want to do with you. Where's it? Okay. Yeah, I want to see if I can squeeze this in here. This is number 3. I'll go ahead and cross off number 3 here. I want to use something that relates to number 4. So let me show you something here. Let's say I gave you a function and use number 3 for this. Let's say I gave you a function y equals cosine of x, and I told you that I wanted you to sorry. I want to just go from 0 to 1. And I want you to use 10 rectangles. Okay. So we're using 10 rectangles to approximate the area under this graph from 0 to 1. What would your width be? B minus A over N, which is 1/10. So your number line could look like this, right? You're starting at 0. What will your next increment be?
1/10,
Followed by
1/5,
1/5. Right, keeps going right all the way until we get to what? 1. Okay. Now, so I can say the integral from 0 to 1 of cosine of x can be approximated using 10 rectangles. What's the width of my first rectangle? 1/10. And what would my height be? Let's say I'm using right rectangle approximation. F of, well, let's say I'm starting with, let's say I'm doing right rectangles. With 1/10. Okay, what's the next rectangle? Well, yes, but my width is still what? 1/10. F of 2/10 plus 1/10 F of 3/10 dot dot dot. What's gonna be the last one?
right?
Right rectangles.
Oh, yeah.
1, right? Okay. So 1/10. This is the same thing. Now, if I were to plug this into the function, what would it be? Cosine of what?
1/10.
1/10. The last one is cosine of 1. Now, I purposely went through that exercise here because I want to show you why things can get confusing. Now, can you look at this expression and know that this is coming from, that you're approximating the area using 10 rectangles from 0 to 1? It's a little harder to see it that way, right? So if you look at number 4 here, it says the expression 1/10 cosine of 1/10 is a Riemann sum approximation for what depth interval? Right. And the struggle is, I mean, obviously it makes sense if we can go from here to here, but can we go backwards? And the struggle that students have with this is they're saying, well, a 10 has to be involved somewhere, right? 10 is just some arbitrary number that we're using to approximate some region. It could be 5 rectangles, it could be 6 rectangles, and that denominator would change, right? So recognizing that 1/10 is not part of my approximation that I'm trying to do. I mean, it is, but that 10 just means I'm using 10 rectangles. So we have to be able to look at this and recognize, okay, that is just some number, right? That 1 is coming from 1 minus 0. My width is 1/10, but really it's my A and B value being 0 and 1. And this 1/10, 2/10, 3/10, that is going from 0 to 1. So the 10 is nowhere to be found if I'm understanding that it just represents the area from A to B of cosine of x dx.
How do you know that
Sorry, my bad, from 0 to 1, the cosine of x dx.
how do you
Yes.
know the endpoints? Okay, 10 over 10, 1, I get that, but
Yeah.
what if I mistake it like for 1/10? Like, how do I know? How do I like? Because it's not telling me right or left, so I don't know, like, subtract 1 from the.
It doesn't matter, right? Well, I think this makes it easier for us to read because we realize that it's starting at 1 and it's ending at 10, so it's the right endpoint. But it's understanding that this is not going from 1 to 10, this is going from 0 to 1 because you're incrementing everything from 0 all the way to 1/10, 2/10, 3/10. That's all increments of within 0 to 1.
Yeah, but like ignoring the previous problem, how do you know that the starting point's 0?
They could have started at 0 and then stopped at 9/10, but it makes it a little bit harder to interpret that way. So if they're asking to interpret, they're usually going to pick the side that feels easier for you to see that connection. So on page 13, sorry, page 17. This is an example of what an AP problem could look like. And here it says the expression is a Riemann sum approximation 4. The confusing part is you look at that 25, you feel like that 25 has to be involved somewhere in my interval, but it's just going to be some arbitrary number, right? This is probably saying that this is only 25 rectangles, right? You're going from 2/25 to 50/25, which is you're really just going from up to 2, right? Because 50 over 25 is just 2. So what do you think your interval is? If your width is b minus a over n, and then if that is just some arbitrary 25 rectangles that we're using, what could be my a and b value that will produce that 2? 2 minus 0, right? And then this square root is just the what? Just some function. What do you think that function is? It's going to be nice and simple. It's just going to be square root of x.
Will this be on free response or just multiple choice?
This is a multiple choice question. Yeah. So you see how that 25 is throwing us off. We said, oh, we got to involve 25 somehow. So if it's 25, maybe it's 50, but if you see that 50 over 25, that's just going from 0 to 2. And if I were to find my increments of 2/25, then it'll be 2/25 under the square root, then 4/25 and 6/25. So this is how this area definition can be worked into an AP problem in this form. Does that make sense?
Wait, so
Mhm.
it's from the intervals from 0 to 25.
Oh, my bad. 0 to 2. My bad. 0 to 2.
Okay.
Just say, yeah. Wait, yeah, okay, okay.
Okay. Page 20. So we have a much more efficient way of finding area under the curve rather than having to go through a limit definition. just like how first semester we found that, okay, there's a limit definition for derivative, which is very inefficient. Then we learned power rule. Same process here. We have something called power rule for antiderivatives, which will allow us to find the area under the curve a lot more efficiently. Now, power rule for derivatives and power rule for integrals are just kind of like a different sides of the same coin. It's the same process, we're just kind of going backwards. So if you think about power rule for derivatives, right, you bring the exponent down and you subtract 1 from the exponent, right? You bring the exponent down and then you multiply with the coefficient in front. And then you subtract your exponent by 1. So if I want to undo this process, rather than subtracting exponent by 1, I'm going to do what? Add. Okay. So imagine I'm trying to work my way back up the chain here. And instead of multiplying, I'm going to do what? Divide. So here's an example here. Let's say my function is x squared. Right? My derivative is just going to be 2x to the first power. So if I'm trying to get from 2x to the first power back to x squared, instead of subtracting, I'm going to add. So I'm going to get 2x squared. And then instead of multiplying, I'm going to divide. So I'm going to take that exponent and divide it out. And that will bring me back to where I started. So we got a little preview into the notation. The notation is with that integral. That integral just indicates that we're taking the antiderivative. And the du is just, it's like d over dx. It's just notation. That du is just part of the notation that indicates the width component of your area. And then you're just working with the height.
Are there no endpoints?
Right now, we call this the n-depth integral. Right now, we're just going to create a rule for area, and then we'll work in the bounds later. Okay. So we're going to add 1 to the exponent and divide 1 by the exponent. And there's also this c, that constant of integration. That's part of the notation. So here you got the integral notation. You got the integrand, which is really the expression that's changing. The dx represents your independent variable. It also represents the width of your area component. And then once you find the antiderivative, then the plus c is something that's going to pop up. It's called the constant of integration. I'm going to talk a bit about what that means. So the question is, well, why do we have that plus c there? Okay. Let me ask you, look at all these functions. These functions all look very similar. They all are x squared and a constant. What's the derivative for my first function? Okay. What's the derivative of my second function? 2x. Okay. What's the derivative of my third function? 2x. So the question is, how many functions share the slope or this derivative of 2x? Infinite, right? It's x squared and some constant. So that's why we say the integral of 2x dx is saying, okay, what function will share this derivative of 2x? It's x squared plus any infinite numbers of constants, right? Because it could be x squared plus 6, it could be x squared plus 5. They all share the same derivative of 2x. So that's why that plus c is there, to show that we have this family of functions that all share the same derivative. So do you remember with power rule for derivatives, we had all these conditions, like rewrite expression as rational exponent, make sure that your variable is in the numerator, and make sure that you expand the terms, remove parentheses before you do power rule. The same conditions apply for power rule for antiderivatives. We have to make sure that each of these conditions are taken care of before we apply power rule for integrals. Okay, so let's go to next page. Let me see if I can go do a couple of examples before bell rings. So again, the rule is we add 1 to the exponent and we divide by that new exponent. So What's the integral of 7? Well, first off, all of my conditions is set for number 1. These are nice and clean. So 7x becomes 7x to the second divided by 2 plus c, because we have infinite numbers of functions that all share the same derivative. Number 2, there's no cleanup issues. Everything is ready to go. Variables up top, no radicals, no parentheses. What's the antiderivative of 7x cubed?
7x to the 4th over 4.
Plus c. So imagine if this was the original function, the derivative of this would be 7x cubed. The antiderivative of 7x cubed would be 7x to the 4th over 4, right? We're able now to go back up the chain where before we only knew how to find the derivative. Number 3, notice every single term is nicely separated. There are no issues with each. We'll just take the antiderivative of each term and treat each like a separate problem. Now, how many C's are there?
What if the 5x 5x?
Oh, fifth. Sorry. Okay, how many C's? 3C. Now, a constant times 3 is still a what? Still a constant. So basically what the reason I want to go through this and just show you that you don't have to worry about adding the C's. You just have to do, you just say plus C once, and that's sufficient to indicate that you've taken care of all the families of functions that can possibly exist. So you don't have to say plus 3C or plus 5C. Plus C is good enough.
3C be 5.
Yeah, it's fine, but I would suggest that you just understand that is just can be clumped together as just a plus C. Number 4, this is not ready for power rule, right? What needs to happen? Boil out. Yep.
Is it like the reverse chain rule?
No, not a reverse chain rule. We do have a reverse chain rule later on called U substitution, but right now we really have to get comfortable with all the conditions with power rule before we can explore that option. Okay, we pull everything out. Now, remember with derivatives, you're stripping away degrees. So a linear becomes a constant becomes 0. So if I'm taking the antiderivative, I'm adding degrees, right? So guess what 1 is going to turn into? X. So every degree is rising by 1. 2 becomes 3, 1 becomes 2. A degree 0 becomes degree 1. A constant becomes, it doesn't go to 0. I think that's the tendency we think, oh, derivative, so 1 goes 0. It's antiderivative, so 1 becomes an X. Okay, there's more power rule conditions I want to do with you. We're a little behind schedule, so I'm gonna see if I can play some catch up tomorrow. But I think tomorrow I'll be able to check your 6.1, 6.2 homework. All right, come with your phones.
Thank you.
Yeah.